Okay, so far with integration we've learned how to use a couple of different methods. We've learned how to use standard results, which are our basics. We've also just met integration by parts and integration by substitution or standard patterns, whichever one you're happy with. We need to have a quick look at how this applies to area. So this part of the lesson is about how to use the things we've already learned to apply to area. You see in this question we're asked this slightly weird question, which is find the area in between these two curves. So we can do this by doing either two separate integrals. So this one on this side is just, if I label this A, well A is this one, and you can take away B. We'll go for this one's B. This area underneath here, G, is B. So we can see this is just A take away B, but we have another option, which is this idea, which is the top take away the bottom inside a single integral. And this is about which one are you most happy doing. Are you happier doing it with a double integral with two things in it, or two separate integrals where you just have to do the two bits separately? And usually in the question one of them will be slightly more convenient, but both of them will be absolutely doable. So maybe you like the look of the first one, maybe you'd rather split it up and do two separate integrals. Maybe that's more work, maybe it's just easier work but a bit more to do. So we're going to have a look at a quick example. I've mentioned here about beware of intersections. Using this method here, it's quite important to realise that this is the top graph, take away the bottom graph. In theory, you could be given a graph where one went like this and the other one went like this. And we need to be a little bit careful because in this first section here, the blue one is the top. And in this second section here, actually the red one is in the top. So here they've swapped over. So if you are using the method of top take away bottom, you need to be really careful about which one's on the top. And make sure that you're computing this integral properly. Okay, let's have a look at an example. So here we get given a diagram, which is lovely. We can pick out there are two intersection points, but actually it's always f of x, the black one on the top, and the red one on the bottom. So that gives us a choice. Choice number one is to do two integrals, and we're going to could do them separately, where we have integral f of x between 0 and pi by 2. So this is integral sine 2x between 0 and pi by 2. Or, and then take away the integral of g of x, which is the integral of sine x cos squared x dx between 0 and pi by 2. So we now have to make a decision. Do we want to do these as two separate integrals or combine them? To me, the first bit is a standard result. So we can do this first bit here, because I recognise sine 2x as one of my standard results. This thing here is not a standard result, but it is actually a substitution one. So I'm going to do these ones separately. You could try and combine them and work out one big integration method for doing both in the same go, but it might end up being more difficult. So this first one we can write out straight away. It's going to become cos 2x between 0 and pi by 2, and at the front we're going to have a 1 over 2 from this 2x in here, so that gives us a 1 over a here, and if you differentiate cos you get minus sine, so we're doing it in minus in here. We're then going to be taking away, and this integral I'm going to have a go out over here, and we're going to use substitution u equals cos x. So if you use u equals cos x, you get du by dx is minus sine x. So if you differentiate cos, you get minus sine. So you get dx is du over minus sine x. And we're going to substitute that in here. So we get the integral from x equals 0. Let's make sure we get the right limits on. X equals 0 to pi by 2 sine x cos squared x du over minus sine x. We get a bit of cancelling here. We get this sine x cancelling with this sine x, and we can actually, if we want, cancel the minus here and the minus here to get a plus. We can now, going back to our definition of u equals cos x, replace this with a u squared. So we have minus a half cos 2x between 0 and pi by 2 plus the integral from x equals 0 to pi by 2 u squared du. Now this bit over here, if we do our u integral, is going to give us 1/3 u cubed by adding 1 to the power, dividing by the new power. And remembering that u equals cos x, this is essentially just 1/3 cos cubed x. Now you might have been able to do this with standard patterns if you're good enough at standard patterns, but substitution is fine. So this equals, we're going to have one big square bracket, 1/2 cos 2x plus 1/3 cos cubed x between x is 0 and pi by 2. We now need to start putting some values into here. I know if I substitute in pi by 2 into cos, I'm going to get 0, because my cos graph, pi by 2 has a 0. So if we put in pi by 2, this first bit here is going to be, the second bit here is going to be 0, and this first bit here is going to be cos pi, because it's 2 lots of pi by 2, which gives us a minus 1. So we get a half here from the minus, and the minus from the bit that's down here, times our 1, plus 0, because cos cubed x for this point here is going to be 0. Take away, and then we're going to substitute 0 into here, so we get minus a half, cos 0 is 1, plus 1/3, again cos 0 is 1. So this gives us 1/2 minus, and in this bracket we have minus a half plus 1/3 is minus a sixth. Altogether this gives us 2/3. If you add on your 1/6, you get to 2/3. So this was a case of, can we decide which integration method to use and whether we want to do it as one big integral or two smaller integrals. Have a go at a couple of these questions. I'm going to pause this briefly. I wouldn't suggest doing 12, 13, 14 of the new spec version, because these are on the stuff that we've not done before. They're on integration of inverse trig. For question 1, they're very, very similar. Just do one of the graphs, and 8 and 9. So 8 and 10 are quite good as challenge questions. So pause it now, have a go at a couple of these questions. Reminder, the online textbook, you can get a link to it on Moodle, and it gives you the information for signing in. For the second part of the lesson, we need to have a look at how you integrate with functions that are given to you using parametrics rather than Cartesian equation. So we're used to finding the area by just integrating y. So Cartesian equation, that's this stuff. This is anything of the form y equals a function of x. You just take your y, integrate it up, and then you arrive at the area. So this is using the chain rule. We're going to replace our dx here with this, which is a combination that cancels down to dx, but this has t's in it. So this says change our integral, just like substitution, from x's and y's into just an integral in t. So this has limits of t equals as well, and t equals. This is a fact that you need to know. It's not in the formula book, so you do need to learn it. So this is any time you have to find an area involving parametrics. Inside this integral, it's not just y and then with respect to x, it's y times dx by dt and then dt. So this is a t integral. One more thing to stress is these limits do have to be t. Again, much like integration by substitution, you cannot go putting in x when it's a u or u when it's an x. So this is just about consistency. Again, this is very little different to the previous stuff. It's just about the initial setup line. So let's have a look at an example. So if we've got our two parametric functions, so we've got x and we've got y, to find our area we're going to use this formula up here, which is our formula for area. These are t limits, so we're going to put this together. So inside our area integral we have area equals the integral from 1 to 2, y is t cubed, dx by dt is actually 10t, because if we differentiate this we get dx by dt is 10t, and then this is dt. So this is actually just a year 1 integral, because this thing in here is 10t to the 4. So we can do that integral. It's just going to go to area equals the integral from 1 to 2. If we add 1 to the power we get t to the 5, and we divide by 5 we're going to get 2 t to the 5. We don't need the integral symbol anymore because we've integrated. Square brackets 2 t to the 5, 1 and 2. Subbing in these limits we get 2 times 2 to the 5, which is 64, take away 2 times 1, which gives us 62. For the other example, here we're given a graph, and we can see this one lands here at 0 and at 9, and these are x equals. And we want to find this area here. So we're going to set our part integral by doing area equals the integral from x equals 0 to x equals 9, and then we've got y, which is 2. We're going to multiply this out, so we get 6t minus 2t squared. So I'm going to put this in here instead. So we've got our x equals 0, we've got our 6t minus 2t squared, multiplied by our dx by dt is 2t, multiplied by 2t dt. Now before I go any further, we've got to look at these limits, because these limits are not t limits and everything else is now t's. We should be able to notice from the graph that these points here are where we get y equals 0. We also get y equals 0 here. So looking at this thing, if I make this equal to 0, I get that t is 0 or t is 3. It's quite nice that they factorised it there, so it means we can see straight away. Tidying up this integral, we get area equals the integral from t is 0 to t is 3 of, then multiplying this out, that minus wasn't very good, was it? Multiplying this out we get 12t squared minus 4t cubed dt. All we have to do now is compute this integral and get to an answer. You might be tempted to chuck this in a calculator, but you're probably going to lose some marks because there's probably some method marks for doing this integral. So we get, for the area, we get square brackets, we get 4t cubed minus t to the 4, so adding 1 to the power dividing by the power, new power, between 0 and 3. We can see the lower limit is 0, and if I sub this in I get an area of 4 times 3 cubed minus 3 to the 4, which is 4 times 27, take away 3 times 27, so we should get 27. I'll just double check this on a calculator in case I've done something very strange. 4 times 3 cubed, take away 3 to the 4, which does give us 27. Yeah. So this was a case of spotting that these limits here, I'll circle them again, are not t limits, they are x limits, and converting these into t's. So this came out to be t equals 3, and this came out to be t equals 0. So the area here is 27. Just going back to the top, this is entirely about setting up this integral. Actually, the integration here isn't very difficult. They could give us parts or substitution. They could set up a weird exact value question. So this can go a lot of different places. The really important step is just being able to go from these things in the question to this integral here, which you can do. So this is the key step for today's lesson. Now, this is actually the extra thing that they forgot when they made the spec. They originally put this in further maths. It should have been in normal A-level maths. So this is the replacement for differentiating arcsine. So this is actually on an extra sheet. You can find the extra sheet if you go on Moodle. If you go on Moodle and go to the textbook section, there's the extra sheet and all the extra information here. So parametric integration was added. See the extra sheet here. The answer to 3b is incorrect. They wouldn't be able to do something without getting at least something incorrect. So the correct answer is there for 3b. I've given you a little pointer for question 1 and question 2 about, in question 1 there's some nasty powers because it says exact value. Loads of people end up with this 4 to the cube rooted all to the power 5 and struggle to turn that into a cube root of 2. So I've given you a quick run through here on how the powers break down. For question 2, if you use substitution u equals cos t and integration by substitution, it works out quite nicely. Have a go at some of those. That'll be just these two things for today's lesson, and we'll have a look at the next bit in the next lesson.